When a sufficiently massive star reaches the end of its life, its core can no longer support its own weight. The star collapses inward, leaving behind a dense remnant with gravity so strong that not even light can escape, a stellar mass black hole. On the opposite end of the mass scale are supermassive black holes. These are the gravitational anchors sitting at the center of nearly every major galaxy, including our own. We routinely observe both of these extremes. We find stellar mass black holes capping out around 100 times the mass of our Sun, and we find supermassive black holes weighing in at over 1 million solar masses. But this creates a timeline problem. We see enormous supermassive black holes existing in the very early universe. For them to get that big, that fast, they had to grow from intermediate-sized seeds. Mapping the transition from stellar remnants to supermassive anchors is essential for understanding galaxy evolution. We need to identify the population that bridges this vast gap in our data. That intermediate population is the intermediate mass black hole. This chart represents the known population of black holes, organized by mass. We have high concentrations on the far left and the far right, but right in the middle sits a huge empty void. Astrophysicists call this the mass desert. This desert spans a specific range, anywhere from 100 to 100,000 solar masses. We have almost no confirmed observations within this entire bracket. Standard telescopes that take static snapshots of the sky struggle to find them. If an intermediate black hole is quiescent, meaning it isn't actively feeding on a massive amount of surrounding material, it emits no light, making it invisible to traditional optical or X-ray surveys. Gravitational wave detectors like LIGO also miss them. The frequency of the gravitational waves produced when intermediate black holes merge falls entirely outside the detection band of our current 4-kilometer interferometers. The mass desert exists because our current instruments are tuned to the wrong frequencies and flux levels. Identifying these black holes require two entirely different observational frameworks. Our current gravitational wave astronomy relies on laser interferometers with arm lengths of 4 kilometers. These facilities have been incredibly successful at detecting stellar mass mergers, but they are rapidly approaching their absolute theoretical sensitivity limits. The first barrier to deeper observation is thermal noise. The microscopic heat vibrations within the optical coatings of the test masses create baseline static that masks faint signals. The second barrier is Newtonian gravity gradient noise. Local seismic activity, the actual physical vibration of the Earth around the facility, couples directly to the suspended test masses. This graph shows detector sensitivity. The curve for our current facilities hits a hard floor, truncating our ability to hear low-frequency signals from the early universe. To push our detection horizon further, we must physically break the 4-kilometer facility barrier. Incremental hardware upgrades are no longer sufficient to solve the problem. Reaching the cosmic dawn requires a massive geometric leap. That geometric leap is the Cosmic Explorer, a next-generation gravitational-wave observatory. The core mechanical upgrade is scale. Cosmic Explorer expands the interferometer arm length by a factor of 10, stretching from 4 kilometers up to 40 kilometers. Expanding the geometry increases the amplitude of the observed gravitational wave signals, but it does so without linearly increasing the detector noise. This chart plots detection reach, comparing signal-to-noise ratio against the universe's age. Longer arms push the boundary deep, crossing redshift 10 into the dark ages. Here we will detect mergers of population 3 black holes, remnants of the very first stars to ever ignite. These primordial mergers represent a primary formation channel for intermediate mass black holes. By listening for these distant collisions, Cosmic Explorer provides a window into the earliest mergers that drove the assembly of the first galaxies. While Cosmic Explorer looks to the early universe, we also have to search our local universe, where older, quiescent intermediate black holes reside in the centers of dwarf galaxies. Historically, astronomers have searched for these using standard static surveys, looking for continuous X-ray or radio emissions. But these static searches run into a wall. The faint emissions produced by a small accretion disk are virtually indistinguishable from local star formation or X-ray binary systems. This creates a physical dilution problem. The ambient optical starlight of the host dwarf galaxy completely overwhelms the faint signature of the black hole hiding inside it. Because our telescopes cannot physically resolve a small black hole from its surrounding galaxy with a single visual snapshot, astrophysicists have to separate them mathematically. We achieve this separation through time-domain variability, a methodology that heavily relies on observatories like the Vera C. Rubin Observatory. The physics principle is straightforward. Steady starlight is consistent, but the light output from an actively accreting black hole fluctuates stochastically over time. Astronomers map these fluctuations using a light curve, a technique rigorously tested on a well-known dwarf active galactic nucleus called NGC 4395. This is a plot of its light curve. By applying a statistical model called a damped random walk process, data scientists can fit a trend line through these erratic data points to identify the underlying mathematical pattern. The critical finding is that the timescale of this variability is directly proportional to the mass of the black hole. Intermediate mass black holes flicker rapidly, over hours to days, contrasting sharply with supermassive black holes on sluggish month-to-year timescales. By monitoring the sky with high cadence over time, we effectively subtract the static galactic starlight, leaving only the distinct, rapid heartbeat of the hidden intermediate black hole. Time-domain astronomy also captures a much more violent signature, the tidal disruption event, or TDE. A TDE occurs when a star wanders too close to a black hole. The immense gravitational gradients stretch and shred the star into a highly luminous accretion disk. Intermediate black holes are uniquely optimized for producing these events because their tidal radii are larger than their gravitational radii. They rip stars apart entirely before swallowing them. As the star is consumed, it creates a massive flare. By measuring the specific rise and decay shape of that light curve, astronomers can calculate the exact mass of the central black hole. A TDE acts as a brilliant temporary beacon, forcing an otherwise completely dormant intermediate black hole to reveal its mass to our time-domain surveys. We now have two highly specialized pathways, gravitational waves and electromagnetic time-domain astronomy, aimed directly at the mass desert. This is the demographic gap we started with. In the coming years, data from Rubin LSST will populate the local side of this gap. Simultaneously, Cosmic Explorer will detect early universe mergers, populating the high redshift side until the mass distribution is complete. These two methodologies operate entirely independently, but they will cross-examine and confirm each other's evolutionary models. Building a complete census of black hole masses across cosmic time allows astrophysicists to refine the timeline of how large-scale galactic structures emerged. By combining gravitational wave data with time-domain surveys, we can finally populate the mass desert, using disparate methods to confirm a single, coherent history of black hole growth.